Okay, in this video, I will talking about back body radiation. So we know that all object with a temperature over than 0 Kelvin will emit energy in the form of electromagnetic radiation, or we call heat radiation or thermal radiation, as you can see in this graph here. The y-axis is the spectrum energy density, and the x-axis is the wavelength. You can see that at the higher temperature, the maximum peak located at the shorter wavelengths. Here you can see the blue line show the higher temperature than the red line, and this back body radiation here, this graph here, can be explained by this equation here, or the Planck's law. Planck is the first scientist who can explain this phenomena by using this equation, and in this video I will mainly focus on how to derive this equation here. To derive this equation, we start with the back body. We assume that it's a cube with dimension L here and have the small opening here. When we put the light into the back body here, it will reflect here, and we consider that at the wall of the back body consists of the oscillator leading to the vibration of the energy here, and the volume of this back body we assume is the L power 3 here. And in the radiation energy for the back body, we assume that the energy of the radiation at the given oscillation is the energy quanta, which is equal to En equal to n h bar omega. N is the quantum number, h bar is the Planck constant divided by 2 pi, and omega is the angular frequency. In this equation is the first time to know that energy is the quantization, as you can see here. So next, to solve this equation, next we gonna calculate the average energy in for the back body radiation. So we can calculate the average energy of radiation by using this equation here. Is the average energy equal to sigma from n0 to infinity, and En and the Fn. Fn is the distribution function of the energy. In a case of back body radiation, Sm is the Maxwell-Boltzmann energy distribution function, which is shown in this equation 1 here. So this is the distribution function of the energy in the back body radiation. Maxwell-Boltzmann distribution is shown in this graph here. You can see that at the high energy, the probability of the oscillation that have the high energy is very low, and at the low energy, the probability of the oscillator that have the low energy is high. And from the Maxwell-Boltzmann oscillation distribution here, we can see we can estimate the C constant here by normalize this equation 1 here. So the sigma, we set this Fn by the sigma from n0 to infinity equal to 1, and you can see here. And then we just move this term to 1 over this term, you can see here. And then we're gonna replace C into equation 1 here, and then replace equation 1 to this equation here. So as a result, the average energy here is equal to this equation. You can see this is the E average energy here, and this sigma from n equal to 0 to infinity here, n equal to 0 to infinity, and En here, En here is the n h bar omega, this is the En, and this term here, this term is the distribution function of the energy Fn here. This is the Fn in the red circle here. This is the Fn from this equation, because it is the Boltzmann. You can see this is the Boltzmann. Okay, this is the C, 1 over C. And from this equation, if we assume that x equal to minus h bar omega divided by kt, therefore we can writing this equation as shown in this equation 2 here. This is the h bar omega here, h bar omega, and then we writing all of the term here, and this is the below term here. And according to this equation 2 here, according to the mathematics, we know that 1 over 1 minus a equal to 1 plus a power 2 plus blah blah blah, and 1 over 1 minus a power 2 equal to here as shown here. And then if we assume a equal to e power x here, therefore by consider this condition, we can replace into the equation 2 here. Finally, we can obtain this equation. So please look in detail. It's not too difficult to understand. And then from this equation here, we can obtain this equation, and then we replace x by this equation. Finally, we obtain here this equation, and finally we obtain the average energy for the radiation from the back body as shown in this equation 3 here. Okay, now we know the average energy for the back body radiation. So next we're gonna derive the spectrum energy density, or mu here. So the spectrum energy density here is the spectrum density of the backbody radiation in a range from F to F plus delta F is the total energy of all oscillation mode in that the frequency range divided by the volume of the backbody. So therefore this energy density can be defined by this equation number 4 here is the energy density equal to average energy multiplied by the number of independent oscillation mode that have the frequency from F to F plus df and divided by the volume of the back body, and the volume of the back body is the air L power 3 because it's the Q as you know is the Q. So L so that's why it's equal to L power 3, and this term is equal to the number of independent modes having frequency from F to F plus df. Okay, so to obtain this one we have to know this term NDF, or the number of the independent modes. We start with the back body. So we know that in the back body the wave that can be in the back body is the standing wave. So the oscillation in the back body can be only the standing wave, as you can see in this image, namely the wave function at the wall is equal to 0, or the wave function at 0 equal to 0, and the wave function SL equal to 0. Moreover, this is the quantized state n equal to 1, 2. So you can see that at the one state is have the two oscillation mode, because it have this one mode, the black line here, and another one is the red line here. So one state have the two oscillation mode, as you can see here, 1 and 2 and so on. And then from the assumption 1, the wave in the back body is the standing wave. Therefore the wave function in the back body is shown in this equation here, consists of kx, ky and kz. Kx is nx pi l, ky ny pi l, kz is the nz pi l, and nx, ny, nz is the number 1, 2, 3 in order to corresponding to this condition here. Okay, and k is the n pi divided by l, where k equal to k power 2 equal to kx power 2 plus ky power 2 plus kz power 2, and n is the n equal to nx power 2 plus ny power 2 and nz power 2. And for the standing wave mode in the back body are represented by the lattice in the positive octant of the space. For example, if we know this, right? So if we make the graph, so this is the ny in z plane, and this is the one dot represent the one oscillation mode. Okay, and then if we want to know the number of the oscillation mode from F to df, so it means this in this area here, in this area. Therefore, since we know that nx, ny, and z have only the positive number, therefore the standing wave mode is show the positive octants of the space. So it will be 1 over s here, because only the positive number in the sphere. And 2 here is mean this one. As we mentioned before, one state has 2 oscillation mode, as you can see here. That's why we put 2 here. And pi 4 pi n power 2 is here, is the surface area of the sphere here, surface area here. Okay, and dn is here. Okay, therefore this is the number of the oscillation mode in F to df. So when we obtain this equation 5 here, we know that k is equal to n pi l. Therefore dk is the pi dn over l, and then we just rearrange to obtain n here, and rearrange to obtain the dn here, and then we replace n and dn in this equation 5 here. Finally we obtain this one. You can see this is the 1 over s 2 4 pi, and this is the n power 2, and this is the dn. Okay, and then we can rewriting this term until we obtain this equation 6 here, where n power 3 is the volume of the back body. And then we know that k equal to omega divided by c. C is the light speed. Okay, and omega is the 2 pi f. Therefore k equal to 2 pi f divided by c. And from this we can calculate dk here equal to 2 pi df over c here. And then we're gonna replace k here into here, and dk here into here, as shown in this one here. This is the L power 3 pi power 2 here, and this is the k power 2, and this is the dk. Okay, and then we can rewriting until we obtain the equation 7 here. And this equation 7 is the number of the oscillation mode in this frequency range delta df here. And then as we know from equation 3, average energy is equal to this equation here. And then from the equation 4, we want to calculate the power density in the df here, as shown in this equation. So we're gonna replace average energy into this one, and this term into this term. Okay, finally we're gonna obtain this one. This is the power density, this is the average energy, L power 3, L power 3. So you can cancel out these two terms, and finally you're gonna obtain the equation 8 here. Okay, and then from equation 8 here, we know that F equal to C divided by lambda, and delta F equal to, and then we can calculate delta A, df as shown in this equation here. and because this is the change, the df, the change of the frequency, so it should not be minus, so we omit the minus sign here until we obtain this one here. So according to equation 8, so we're gonna replace df by this equation here, and then replace f by c over lambda. Finally we obtain this one here, and then we rewriting again until we obtain this equation here, and then if we omit d lambda here, finally we obtain this one. This is the result that we would like to obtain, that is the Planck law. So according to the black body radiation, this is the first time to use E equal to HF. Okay, thank you very much.